Hello everyone, thank you for having me today. My name is Tintin. I am currently working in Forrester's Financial as an actuarial analyst. Today, I want to introduce you a topic related to generalized additive modeling applied for the accurate estimation of insurance claims. Specifically, I will walk you through a simulation study to demonstrate how GAM gives a better fit than the parametric GLM for the simulated insurance claims dataset. Please note that this research was co-authored by Dr. Peter and Dr. Desmond. So without further ado, let's get started. This research aims to relax the assumptions on the GLM's linear predictors. As known, the linear predictor of GLM is only constrained to a linear and parametric form. So we were thinking of including some sort of smooth functions or smoothers to estimate the loss cost. In other words, we want to extend the framework of GLMs to a framework of GAMs in modeling the expected loss cost to allow for more flexibility like non-parametric and/or strongly nonlinear trends. By doing this, the insurance companies can more accurately estimate the expected loss cost and then more adequately price the insurance premiums for each risk class. As a result, it can protect the insurers against adverse selection and also help it find its niche markets to operate more competitively and profitably. In order to quantify and illustrate the GAM fittings, we carried out a simulation study for 1,000 iterations with 10,000 cases per iteration. As the insurance companies usually do, we define the loss cost as the expected claim count multiplied by the average claim size. So first, we simulated a claim count which follows a Poisson distribution. And then, given the simulated claim count, we generated the claim size for each claim using a pre-specified gamma distribution. Please note that we artificially added the nonlinear components to both the claim frequency and severity's linear predictors. And there is also a dependent structure, beta n, introduced between the claim frequency and severity. Due to the time constraint, we won't discuss it further, but I just want to make you aware of this. Then we use the cubic panelized regression spline to fit both the claim frequency and severity models. This specific spline will be explained in the next two slides. Finally, we leveraged the graphical diagnostics AIC and the hypothesis testing to compare the parametric GLMs with the GAM fittings in modeling the loss cost. And based on the results, we will make our final conclusion. In this research, we used a very popular smoother, so-called cubic regression spline. It is a compromise approach between the parametric and non-parametric model fitting. It has several advantages like computational cleanliness. And more importantly, we could use the standard parametric inferential methods to test the significance of the parameters. This will make us interpret the results much easier. However, this approach do have problem or difficulty in choosing the proper number and/or position of knots. In order to overcome that ordinary cubic regression spline's main drawback, we use the cubic panelized regression spline throughout this study. By introducing a smoothing parameter lambda, it will make a necessary trade-off between the smoothness and wiggliness of the model fit. That is to say, the selection of the number and position of knots would have very limited impact on the model fittings anymore. Instead, the lambda will do the sensible work to control the degree of model smoothness. With the study purpose and the methodology explained, we now can readily look into the study results. The table on the top shows the claim frequency model's intercept estimate and the estimated coefficients of x1 and their standard errors. The estimated coefficients of x1 and their standard errors for both frequency GLM and GAM look identical. But the frequency GAM's intercept estimate is clearly closer to the true value 1, and its estimate also has smaller standard error. However, as you can see, there's still an approximate 0.4 unit discrepancy between the GAM intercept estimate and the true value. We will get back to this point in the next 2 slides. The bottom table shows the adjusted R-squared and AIC for both of the frequency models. The higher adjusted R-squared and the lower AIC value for the GAM fitting both indicate it did a better job in modeling the claim count. Remember what I mentioned in the previous slide about the 0.4 unit discrepancy on the GAM's intercept estimate. As looking at the GAM fittings of X2, there seem to have a 0.4 unit downshift from the true function. So we were guessing the vertical shift of the GAM estimate is due to the choice of the spline basis function. After shifting down the real function of x2 by around 0.4 unit, the GAM estimates of x2 can almost overlap the true function. So this confirms our previous conjecture. The downshift of the x2 GAM fitting can be compensated by the same amount of value added to the intercept estimate. This plot also demonstrates the GAM fitting did a very good job in modeling the claim frequency with some nonlinear trends in it. We also used the approximate f-test and the parametric bootstrapping to test whether the smoothing of x2 is necessary. The very small p-values from both tests indicate strong support for rejecting the non-model. Thereby, we can conclude that the smoothing of x2 in the claim frequency modeling is necessary. Due to the limited number of Poisson responses, the discreteness occurs in the deviance residue plots, so it is not very helpful of checking the model fits in this case. Compared with the deviance residue plots, the partial residue plots can be more useful in this case. It shows the relationship between each predictor and the response variable given that the other predictors are in the model. As shown in the plots, the GAM fitting of x2 is more evenly scattered around the curve to which it relates, and it more correctly captures the true trend of x2. As I mentioned in the methodology section, we've introduced a dependent component to the claim severity model. Although we don't have any time to discuss the dependent settings, the results can be readily read off from the standard error plots for both the intercept and the coefficient of x1 for the severity models. Clearly, no matter under which dependent setting, the GAM fitting always gives a smaller standard error than its corresponding GLM fitting. Here, I want to show you some examples of the partial residue plots for severity models under certain dependency level. Don't be too bogged down by the dependency structure. The more important thing is to see the comparisons. The GAM fitting seems to make a good transformation of the predictor x2, as the fitted curve correctly captures the trend of x2, and the partial residues are evenly distributed around the fitting. While the GAM fitting of x2 appears to be inadequate, since the pattern is not well described by the fitted lines. The severity GLM's deviance residues have some tapering and nonlinear patterns, while the severity GAM's deviance residues are more compactly distributed around zero, which indicates homogeneity of variance. Overall, the hypothesis testing, AIC, and diagnostic plots all indicate the GAM models do give a better fit than the parametric GLM approach in the insurance claims estimation. Thank you for your attention today.